Hello, in this video we're going to take a look at a moderately difficult optimization problem, the problem of the conical cup. So we're going to start with a circular piece of paper that has radius r. So this capital R is going to be fixed through this problem. A pie-shaped sector with vertex at the center of the circle is cut from the circle. This piece is then folded and glued to make a conical cup. We want to find the maximum possible volume for this cup. So here is the circle with a sector cut out. So we've made these radial cuts perhaps along here, and then just pulled this sector out. And we're then going to imagine folding that sector into a cone. So this piece of triangle that we just tape these two edges together and get the cone over there, which you're going to call a cup. We want to maximize the volume of this cup. Now this cup is a cone, so we need to work with the elements for the volume of a cone. That is the radius of the base, or in this case the opening of the cone that R, and the height of the cone or cup, which we'll call H. So we're going to have to find expressions for those in terms of some variables we control in the problem. So the only thing we have control over in this problem when we make the cut is the angle of the cut. And that's this angle here, which we're going to call theta in just a moment. So we'll decide how big that angle theta should be to give this cup of maximal volume. So we've gone ahead and put the theta on the picture here. And we'll find that when we bend that cup, that sector into a cup, that this circular part of the cut, of course, becomes the rim of the cup up here. Now you may recall from geometry or perhaps analytic geometry that if you have a sector of radius r and angle theta cut from a circle, the length of the arc you get is then just found by doing r times theta. This assumes, by the way, theta is in radians. And the reason for that is this, that a sector is theta over 2 pi of a whole circle. A circle has 2 pi radians. So that means that this arc here must be the fraction theta over 2 pi of a full circle. So the arc length is then going to be this. It will be theta over 2 pi of the whole circumference, which is 2 pi r. And you can check that when you do some cancellation, you come up with r theta for the length of that arc. So that's going to be an important quantity here. We're going to use that to get the radius of the cone. So we'll go ahead and put the r theta on our picture. And we now know what the circumference of that rim is. So the theta is a variable in this case, but remember the capital R is constant because it is the radius of the disk we started with. Now let's let r be the radius of the circular cup opening, as we illustrated earlier, and h be the height of the cup. So we're going to put those into the picture. The r is going to go like this, and the h here, and we'll find we have enough information to express r and h in terms of theta, which is going to be our variable for differentiation. So in the next picture, we've actually put those elements in. There's the r and the h. We've made a bigger picture here. So what can we say about r and h in terms of the variable theta over which we have control? First of all, we notice that, again, we have the circumference of this opening. The circumference of this opening of the cup is r theta. On the other hand, if this opening has radius little r, then this circular opening also has length 2 pi r, the circumference of the circle. So it must be that 2 pi little r is equal to capital R theta, and we can then solve for little r, and there's our expression for the radius of the cup opening in terms of the angle theta of our cut. For the height, we just use the Pythagorean theorem. So we're going to work with this right triangle here with one leg r, which we now know, one leg h, and the hypotenuse is this radius of the original disk, which is capital R. So we can see by the Pythagorean theorem, h squared is capital R squared minus little r squared. And if we solve for h. H is the square root of capital R squared minus little r squared. And for our next step, we then use the fact that we know what little r is in terms of theta, and we make that substitution for little r. And then a little algebra. Each of these factors under this radical has an r squared factor in it, so we're going to pull that out, factor that out, and bring it outside the radical as an r. And so here is an expression for the height of the cone. So we now have the radius and height, and we can proceed to look at the volume. So we've worked with cones in class before, and we know that the volume of a cone is given by 1/3 the area of the base, that's pi r squared, times the height, which is h. So all we have to do at this point to get v as a function of theta, because it's the theta we're curious about, is to replace little r by the expression we found over here, and h by the expression we found up here. So making those substitutions brings us to this expression for v. So we've just copied the v expression there, and we can do a little algebra on this. What we did here was we just took that square to get r squared theta squared over 4 pi squared, canceled this pi out here with one of the pi's in the denominator, and then finally brought the r's together for r cubed, and then added these fractions under the radical. When I add the fractions under the radical, I have 4 pi squared minus theta squared over 4 pi squared. And when that's under the radical, this 4 pi squared comes outside as a 2 pi. And that's what bumps the denominator up to 24 pi squared. So you can work through that algebra, double check it if you like. Finally, so we now have the function we wish to maximize, this volume formula. And what are the allowable values for theta? Well, since theta has to come from that circular sector, or that circle, rather the disk that we showed earlier, radius r, we know that the angle for theta has to be somewhere between 0 and 2 pi. We can't cut any more than a whole circle and can't cut any less than a 0 radian angle. So this is good for us. It's always nice to have a function, continuous function, which we have here, that we want to maximize on a closed interval, in this case 0 to 2 pi. Again, this is nice because in section 4.1 we learned that a problem like this always has an answer. There is a maximum value, so we know we will find an answer for this problem. Now, this function, the derivative exists everywhere. Okay. It's involving square roots and powers of theta. And so we're going to find the critical points by finding the derivative and setting the derivative to 0. Now, when we do the derivative, keep in mind this is a product. It's the function theta squared times the square root. Also, r is constant. So the factor r squared over 24 pi squared is a constant multiple in front of the problem. So we can use the constant multiple rule and hold that in front of the derivative when we take it. So here's our product rule application. Here's the constant that we're going to hold out in front. The first function is theta squared, so there's its derivative times the second. Then we have the first function theta squared, and then the derivative of the second. There's the product rule. Evaluate these derivatives. The theta squared becomes 2 theta on differentiation. For the 4 pi squared minus theta squared to the 1/2, we have the chain rule. It's the 4 pi squared minus theta squared polynomial composed with the square root or 1/2 function. Differentiate the 1/2 power, get 1/2 4 pi squared minus theta squared to the minus 1/2, and then the derivative of what's inside gives the minus 2 theta. So there is the chain rule. Now, because we have to work with this derivative, that is set it equal to 0 and find the zeros, we really can't stop here. We have to do some simplification. So this takes a little algebra, which you're going to jump to. We've written it in a couple of steps here. So we've kept the multiplier out in front, Haven't done anything with this first term. In the second, we've consolidated some terms. The 1/2 and minus 1/2 down here cancel. And we have a theta squared that goes in the numerator up here. Here's the minus sign that we see down here. And then I've just put the square root into the denominator. Now finally, our next step, we add these two fractions by constructing a denominator of root 4 pi squared minus theta in the denominator. So we multiplied the top and bottom by this square root that we see right here in the denominator. And that gives us a common denominator, allows us to add the fractions and get out some paper and test this, but this whole expression simplifies to this. So that is a simplified form of the derivative and one we can actually work with when we go to set the derivative to 0. So here is that derivative. And again, we want critical points for v, so we set this derivative to 0. Now this is a complicated looking expression, but we know that for a fraction to be 0, its numerator must be 0. So thus we only have to worry about the numerator up here. This is the only part that has to be 0 to make the derivative 0. So we pick that off, and we just have to solve the equation 8 pi squared theta minus 3 theta cubed equals 0. And this is easily done by factorization. So we factor out the theta, and then we can either have the theta out in front equal to 0, which is this first root, or we can have 8 pi squared minus 3 theta squared equals 0, and solving for theta gives you these two values. Interesting to note here, by the way, that these critical values are independent of r. Notice there's no capital R in those equations. When you think about the situation, whether the disk is small or large, we expect we'd have to make the same angle for the maximal cut. Okay. Now remember, we're working on the interval from 0 to pi. So any theta outside that interval is one we need not consider. And that means we can throw out the negative potential critical point. So we have these two critical points, one of which happens to be an endpoint. And there's one more endpoint. So including our endpoints, we see we have 3 candidates for the angle theta of the cup that leads to a cup of maximal volume. So theta is the angle of the cut, and that will lead to a cup of a certain volume. So once we have 3 candidates, all we have to do is plug them back into the original function. So here is our formula for v, and see which of those 3 gives the largest value. Now, if you think about the geometry of the problem, it's pretty clear that if you make a 0 radian cut, which gives you nothing, you get volume 0. And if you make a theta radian cut, which just means you're going to take the whole disk and fold it into a cone, you're again going to get a volume of 0. And that's borne out if you actually plug 0 or 2 pi in for theta into this expression. You'll see that these do come out to be 0 in each case. So the third value is the one, of course, that we're going to be interested in. And just to make sure everything is working here, let's now take the critical point 8 or pi times square root of 8/3 and plug it into the volume formula. So we have the multiplier r cubed rather over 24 pi squared. And then when we plug in this value 8 square root of 8/3 for theta squared, in theta squared here we get pi squared times 8/3. And then finally here is the theta being put in for the theta squared under the radical. Again, we'll leave the algebra up to you, factoring pi squared under the radical, adding those fractions under the radical together and doing a lot of cancellation. We see that this comes out to be 2 square root of 3 over 27 times pi r cubed, which is about 4/10 of r cubed. And so this is the maximum possible volume for the volume of the cup. We could be done here, but let's go on and just talk about the solution a moment. So this conical cup we found has maximum volume if the cut is made with a sector of angle pi root 8/3, that's about 1.663 pi, or about 5.13 radians. Now remember, a whole circle is 2 pi, so this is bigger than 1.5 pi, so we're actually making a cut bigger, a little bit bigger than 3/4 of the circle. So that's a pretty big cut, pretty big angle. Just to kind of see what's going on, again, you don't have to do this, but I think it's always a good idea to double check things however you can. Down here, we've graphed the function v of theta equals r cubed over 24 pi squared, etc. This is the function we're trying to maximize. I took r equal 1 when I did this, okay, because we have to know what r is to produce the graph, and we found things were independent of r. And if we put r equal 1, we see that the maximum does seem to occur about here, a little bit bigger than 5 radians like we thought, and the maximum value up here, pretty close to 4/10, maybe a little bit bigger. So this graph kind of confirms our calculations and shows that for the maximum, we want a sector of about 5.13 radians, which seems pretty big. So this is what the cut would look like. So if you'd like to see what this looks like, I have here a cut I made from a circle. This is 5.13 radians, so this should make a cup of maximal volume. So I'm going to use some tape, as you see here, and put our cup together. So I'll bend it like this to get the edges in good shape, and then put some tape along here and secure it. And so there we see what the cup looks like. It's a pretty big radius. Not very tall, so it has a lot of volume, but probably would be kind of difficult to drink out of. But looks like it makes a pretty good hat, and it's in cyclone colors, so maybe we'll use it in that way instead. By the way, if you too would like a cyclone hat, I have 2 more cyclone hat kits. Here they are. And if you'd like one, just write to me at this email address, and in your subject heading put cool hat, and then your TBL instructor, which will be Johnston, Bowles, or Peters. We'll then make the presentations in class. You do have to be present to win, so even if you're one of the first 2 and not there, we'll give the hat kit to someone else. So this is your chance to get something free out of this class, and something that you can actually use and wear around campus. So hope you enjoyed this video, and good night, and we'll see you in the next one.